Hello, everyone. My name is Swaechchha, and I am a PhD student at University of Southeastern Norway and Kathmandu University. It's a pleasure to be here today to discuss my work on enhancing power system efficiency in the Nordic region. Now, to set the stage, let me start with a scenario that many of us can relate to. So let's imagine it's a cold winter evening in Stockholm. Millions of households are turning off their heaters simultaneously, and the demand for electricity surges dramatically. Meanwhile, in Norway, abundant hydroelectric power is available, but transmitting that energy efficiently to where it's needed most is a complex challenge. The importance of balancing supply and demand across the Nordic grid comes into sharp focus. Now, this scenario is not hypothetical, it's a reality that grid operators face regularly. Talking about historical lessons, in 2003, a massive blackout swept across parts of Italy, leaving 56 million people without electricity. Can we guess one of the culprits? It is inefficient power flow management in interconnected grids. So while the Nordic countries have robust systems, they are not immune to such risk. The complexities of managing power flow in a grid that spans multiple countries and diverse energy sources present ongoing challenges. So, efficient power flow management is not just a technical concern, it's a societal imperative. And as a global community accelerates towards sustainable energy sources, the reliability and efficiency of our power grids become of high importance. Transmission losses does not just mean wasted energy, they translate to higher cost for consumers and increased environmental impacts due to the need for additional generation. In an interconnected system like Nordic Grid, optimizing power flow is very much essential for energy security, economic stability, and achieving our climate goals. So, with that background, let's talk about the solution space. I'll share with you how advanced metaheuristic optimization algorithms, specifically particle swarm optimization, Cuckoo Search Algorithm, and gray wolf optimization, which are developed in different time frames and hence the reason for comparison, can assist power flow management in the Nordic grid. Now, metaheuristic algorithms are powerful tools that help us navigate complex optimization landscapes where traditional Newton-Raphson methods might fluctuate. Particle swarm optimization (PSO) is a population-based optimization algorithm that maintains a set of candidate solutions, which are called as particles. That move through a search space in search of a optimal value. So the algorithm starts with initial population or like initial particles, and they are randomly initialized with a given search space, and it works by iteratively updating the position and the velocity to find like the optimal solution in the space. Similarly, CSA, Cuckoo Search Algorithm, is also a population-based optimization algorithm, but they are inspired by cuckoo species laying their eggs in the nest of other species. So the nest represent candidate solution, and the cuckoos represent the new solutions generated by the algorithm. In the same way, GWO simulates the social structure and hunting habits of wolves in the wild, where each wolf represents a potential solution to the optimization problem. So, by applying these algorithms, we aim to identify which method offers the best performance in terms of loss minimization and efficiency improvement in the Nordic grid. Now, the OPF problem seeks the optimal settings for control variables to achieve a specific object, which in my case is minimization of real power losses in the system. Now, the total power loss is calculated using the equation shown here. where the terms represent the relationship between voltage magnitudes and angle at different buses, also the conductance of lines connecting them. There are also certain constraints that we must respect. So generator output must remain within their minimum and maximum limits to ensure safe and efficient operation. Similarly, voltage levels at each bus may stay within prescribed bounds to maintain system stability. Now, these constraints make the OPF problem very much nonlinear and complex. And that is precisely why we are using meta-heuristics like PSO, CSA, GWO, because they are good at finding optimal solution in such challenging optimization landscapes. Now, to validate their effectiveness, we first tested the algorithms on standard IEEE test systems of different sizes. So IEEE 14, 39, and 118 bus system. Now, this step is important because the benchmark systems are widely used in power system studies and provide a solid foundation for assessing optimization methods. So, in summary, the experiments on this test system show that GWO, which is the purple line in the plot, it consistently provides better performance in terms of convergence speed and loss minimization. Now, CSA also performs competitively, especially in the larger systems, outperforming PSO. So overall, all the meta-heuristic algorithms outperform these Newton Raphson methods in reducing the total system losses. Now, these like preliminary results are encouraging and demonstrate the potential of using meta-heuristic algorithms in power system optimizations. Moving forward, we applied those meta-heuristic optimization algorithms to the reduced Nordic 44 pricing area model or reduced N44 PAM. Now, this model is this is the model that we can see. So this model is a modified version of Nordic 44 model, updated to reflect the current and the proposed network topology of Norwegian and Swedish power systems. And this represents a downscaled version of the anticipated 2030 Nordic grid, incorporating planned expansions to accommodate growing electricity demand. So the detailed system parameters are in the paper if any of you is interested on the the parameters of the model itself. So in our analysis, we conducted 3 case studies to test the effectiveness of our proposed approach under different scenarios. Like so the 3 cases were base case, light load case, and heavy load case. And they were different in like the base case was 75% load and without import and export. This is like the fundamental study of the system. And light load case is a scenario with like maximum exports from Norway and Sweden and with 50% load. And the heavy load case actually represents like the winter time where 90% of the load with some import and export. Now, if you look at the plot, we can see that in the base case scenario, all 3 algorithms produced similar results with GWO performing with 11.5% and 3.6% better than PSO and CSA respectively. So similarly, in like heavy load case, GWO still achieved like the lowest power loss among 3 algorithms. Also in light load case, GW performed the best results, while CSA showed the worst performance with only 6.9% loss reduction than the Newton Raphson method. So overall, the results demonstrate that GWO algorithm is like the most effective approach for minimizing power loss in the reduced Nordic 44 model, particularly in scenarios with like high load and high hydroelectric generation. Now, these tests aim to demonstrate the robustness of our method in managing power flows between Nordic pricing areas, like under varying operational conditions. Now, beyond minimizing power losses, it is also very much important to understand how the optimization impacts other significant electrical parameters that affect the overall performance and reliability of the power system. Now, this slide here focuses on the uh, impact on electrical parameters, specifically line loading, generation distribution, and voltage angle distribution. So, okay, briefly, line loading is a vital parameter in power system analysis, and it determines the amount of current flowing through a transmission line relative to its thermal rating. So, high line loading can lead to high transmission line losses and failure, voltage instability, and sometimes like even blackout. So, if you see in the plot, so this analysis is done for like the base case scenario, and so when we see this plot of line loading percentage, we can see that the line loading reached up to 140 percentage, which is like significantly exceeding safe operational limit when using Newton-Raphson method. Now, utilizing the proposed metaheuristic algorithms, we have substantially reduced the line loading to a range of like 100 to like 30 percentage across the same set of lines. So the GWO stands out, recording the lowest mean line loading like at 31.06 percentage and standard deviation of 21.35. So this shows the balanced power distribution and like focuses the superiority of metaheuristic methods in complex power system optimization. Now, if you look at the generation distribution and voltage angles in here, bottom right, um, so while with the metaheuristic algorithms, we can observe an increase in generation at slack bus. So which we did this SE3 is a slack bus in my model, and we can see that the blue line is neutral adaptation, but the other lines they are above the blue line. So and the metaheuristic algorithm actually increases the slack bus generation. And this as adjustment boosts efficiency and stability as the algorithms dynamically allocate power generation to achieve a global balance. Uh, Moreover, the generator voltage angle, which indicates the phase difference between generator and load bus voltages, directly influences power flow and system stability. The results show that with metaheuristic algorithm, the voltage angles decreased, and this reduction reflects algorithm capacity to fine-tune power flow in the transmission lines. So, in conclusion, the study presents a comprehensive analysis of metaheuristic algorithms, specifically the three algorithms that we have used, PSO, CSA, and GWO, in optimizing power flow within the Nordic pricing areas using the Reduced Nordic 44 pricing area model. The findings indicate that GWO algorithm exhibited like superior performance consistently, outperforming both PSO and CSA across various test cases. Um, Also, the application of GWO led to a significant reduction in line loading, achieving the lowest mean line loading and standard deviation. So this suggests that like GWO is more consistent and efficient power distribution throughout the network. Now, the findings actually have important implications, I believe. They suggest that meta-heuristic algorithm can significantly improve system efficiency and reliability. And by optimizing power flow to reduce losses, the algorithm saw like promise in enhancing economic aspects of power management, potentially lowering electricity cost for end users. However, integrating these algorithms into the operational power system is challenging, and it must consider existing infrastructures, operational protocols, and the training of personnel. Now, the scalability of this algorithm is a major challenge in real-time settings where we have to make the decision like really quickly. So, additionally, also integrating these algorithms into current grid management systems, which often rely on traditional techniques like the Newton Raphson algorithm, it also presents like the further challenge to integrate metaheuristics in for like real-time setting. So, therefore, while the research demonstrates the potential of metaheuristic algorithms in powerful optimization, their practical application requires careful consideration of technical, operational, and regulatory factors. So that was all for today. Thank you so much for your attention. If you would like to continue the conversation or have any further queries, please feel free to email me, or you can also use this QR code to connect with me on LinkedIn. Thank you so much and hope you have a good day.